Hello guys, my name is Carlos Ramirez. The topic I chose for my presentation is underground transmission lines. A quick summary of my presentation. I went over two papers. The first one was on underground transmission lines, which basically introduced gas insulated lines. What these are made up of is basically two concentric aluminum tubes and an inner conductor resting on resin insulators and a filled mixture of nitrogen and sulfur hexafluoride. The second paper, I was looking for a method that would look for faults in the actual underground transmission line, since it is very hard for companies to find out where exactly the fault is. So the actual methods that they used in the second paper was algorithms introduced into MATLAB and Simulink, and then later on treated onto Google Maps. The reasons why I chose this topic, guys, it was basically in relevance to the course. Since we did go over transmission lines, I was a little bit more curious about them. I was also concerned with the safety, since overhead transmission lines can happen to be very dangerous during extreme weather conditions. The cost and efficiency were of course main priority in these papers, so that was introduced to me, and that of course made me want to explore more of the actual methods. For my extrapolated conclusion, I basically got from this that underground transmission lines can be installed in various methods, and of course it is always better to be safe in your actual maintenance of these transmission lines. That is why gas insulated lines happen to be very good for safety reasons. Already with 5 decades of successful installation and running energy, the gas lines have proven to us that they're a pretty good method for this. I also saw that the software and development in the fault search can bring our power back up and running in the shortest amount of time. So for the introduction on the gas insulated lines, they were introduced in 1975 in Germany, and they are still running up until present day. Actually, more than 750 kilometers of gas insulated lines are running all across the world, and the maximum operational voltage for these is 550 kilovolts, and with a maximum operating current of 5,000 amps. Advantages for these, as I had said, it is low transmission losses, low capacitive load, negligible electromagnetic fields, no maintenance in 50 years and plus, and high reliability and high level of personal safety. Here we have the basic design. You have the outer housing made up of aluminum. You have the aluminum conductor in the center, which is resting on the insulators. You have a particle trap for any escaping charges. And of course you have the insulating gas made up of nitrogen and sulfur hexafluoride. And for the installation, there's basically 3 main types. The first one I saw was the incline tunnel. You have the lines basically going in, of course, into a tunnel and on an incline position. These lines can have a bending radii of 400 meters, and for smaller radii, they have special elbows, which of course can bend up to 90 degrees. The second type of installation is a tunnel installation. This type of installation is mainly focused on safety. It is accessible for the workmen to actually come in here and fix whatever faults there might be underground, of course. The lines that you have here are for 420 kilovolts and a bending radius of 400 meters. The third method that we have is directly buried transmission lines, introduced into 2010. It is the fastest and most cost efficient method. Now for the actual setup, as you can see, you have the exact same design here, your conductor, your aluminum cover, your insulators, and this disc that we see right here, they call it the fixed point insulator, which they install at every 120 meters. And these, the gas insulated lines, it's basically already made up, and what they call a mobile factory that we'll see later on. These are actually made up on site. You have the production and the installation right on site. Okay, so this is what they call the mobile factory. This is the side view of it. As you can see, here's the production of the gas insulated line. And as I had said, it is prefabricated on site. They also do the welding, they do the loading, and thanks to these factories, you have project duration and project cost significantly reduced. I had read that a new automated welding process is under development and promising welding connections faster by a factor of 3. Here we have the front view of the factory positioned in the trench, and what they mean by the trench is that they're basically doing the directly buried method. You'll see that the lines are gonna be just laid up on what they call the trench, and of course they will be covered. What they focused on mainly is the welding process, since it is very important that they weld it right the first time. I read that having to do a rework on them will actually take up time and be, of course, more expensive for the company. The quality of the gas type welds is very important, as it is the main focus of the company, since you don't want to have so much maintenance going on. You want the gas very locked up very good in these. Okay, so the paper also talked about the development of 500 kilovolt direct current transmission lines, and as you can see, like I had said, you have a trench, you have your DC lines, your positive, negative, of course, and you end up covering it with concrete. You have measurements right here of what goes exactly where. And of course, they are trying to reach a potential of 5 gigawatts of electrical energy. Here we have a comparison of the AC and DC lines. This is what they started with. These lines are the actual insulators. What we have here is basically saying that that the capacitive resistive field transition is accompanied by the accumulation of charges along the surface within the bulk of the insulation. And what I depicted from this is that here the insulators are not being affected as much, but here you are building up your field of capacitance and which ends up becoming resistive. Okay, the tests that they tried applying on the DC voltage lines are basically tests of direct voltage, impulse voltage, and heating of the conductor. Now moving on to the fault locating methods, they started off with a single-ended fault location algorithm, which they called, and here you have the schematic. You have the sending bus, over there on the R is the receiving bus, which ends up being basically the start and end point of the transmission line. They simulated here the ground fault, of course, right there in the middle of the line, and they basically focus with the impedances of the sending and the receiving bus. You have your voltage over current. Now what they call the Z line is the impedance per kilometer. Using this, of course, you end up getting your distances from the sending end to the fall point of or the distance from the end to the fall point. They also have the double-ended unsynchronized fault location algorithm. The concern with this method was still not good enough. The first method, which is the single-ended, was not very good since it did not take fault resistance and shunt capacitance into consideration. But the double-ended unsynchronized, still not good enough for the underground transmission line since you have a higher shunt capacitance. Now for the last algorithm, they called it the double-ended synchronized fault, and it basically, it was the most accurate method that they could use with the actual fault search. Here they have their system set up. And so basically when the fault occurs, you would see that these equations, number 10 and number 8, they would end up being similar. And from there you can calculate your location index. Here is, they are using Simulink to model the transmission line. You have your sending end, your receiving end, and throughout the transmission line you have your measurements. As you can see, these are the parameters that they inserted into MATLAB. They then use discrete Fourier transform to calculate the fundamental voltage and current phasors, and after that they ended up testing each of the algorithms to see which one will give them the most accurate results. Here are the table of the results. You have the single-ended, the double-ended unsynchronized, and double-ended synchronized algorithms. You can see that these are the fault distances. You have your estimation results, and as you guys can see, they vary a lot. Here the double-ended synchronized algorithm, which they did mention that it was the most accurate one. You can see the differences in the results of the distances. Okay, so here are the actual parameters of the underground transmission line, where you have the total length, your impedance, your line inductance, and your shunt capacitance. Here the double-ended synchronized algorithm indicates that the fault distance is the most closest to the 1.3. Now, after collecting their data from their algorithms and softwares, they use Google Maps to actually portray where the actual fault is. This test was made in Taiwan from 2 substations, and they located their fault point right here. Okay guys, but that's basically it. These are my citations, and